The closest point is 53.445 million kilometers. Jupiter's Hill radius, the boundary where its gravity overrules the Sun, is 53.502 million kilometers. The margin between those two numbers is 57,000 kilometers. That's roughly the diameter of Jupiter itself. Today is the day those numbers stop being theoretical. I want to be careful here because most of what you've read about 3I Atlas has framed this as a proximity story. How close the object gets, what we might see, whether Juno has enough fuel to look. That framing misses what's actually interesting. Jupiter in this encounter is not a backdrop. It's a scale. Let me explain what that means. Every object with significant mass carves out a gravitational domain. Inside that domain, the object's own pull dominates over everything else. For Jupiter, that domain, the Hill sphere, extends roughly 53.5 million kilometers in the direction of the Sun at this point in its orbit. Anything passing through that volume will have its trajectory bent by Jupiter's gravity along a curve that is, in principle, completely predictable. You know the incoming vector, you know Jupiter's mass, you know the laws of motion. You can calculate exactly what path the object should follow on the way out. If it follows that path, the model holds. If it doesn't, you've just learned something about the object that no spectrograph, no light curve, no activity measurement could tell you directly. That's the measurement, not a press conference, not a telescope image, a deviation, or the absence of one in a publicly accessible ephemeris database. The reason this matters is that we don't actually know how massive 3I Atlas is. That sounds like an oversight, but it isn't. It's a fundamental constraint of how we observe things at interstellar distances, and it's worth spending a few minutes on. When 3I Atlas was discovered in July 2025 by the Atlas Survey at the Rio Hurtado station in Chile, it was immediately flagged as unusual. The orbital eccentricity came in at 6.141, compared to 1.2 for Oumuamua and 3.4 for Borisov. This object was moving through the solar system on a trajectory that could only have originated somewhere else entirely. The speed at perihelion was 68 kilometers per second. It wasn't passing through. It was transiting. Over the following months, 227 observatories submitted data. By September 2025, there were 4,022 individual observations on record. And in that entire dataset, across 4 months of continuous tracking, there was no detectable non-gravitational acceleration. None. The object moved exactly as gravity predicted, to within 0.028 arcseconds. Then it reached perihelion. At perihelion, something changed. Davide Farnocchia at JPL, using ALMA data, detected a 4 arcsecond offset in the object's right ascension relative to a pure gravitational trajectory. That's a non-gravitational acceleration. It became measurable at 89.3 plus or minus 4.6 times 10 to the minus 9th astronomical units per day squared at its peak. The object was no longer moving purely under gravity. The standard explanation is outgassing. The Sun heats volatile ices. They sublimate asymmetrically, and the escaping material acts like a weak thruster. Comets do this. It's well understood. Almost certainly, there's a mundane explanation along these lines. But consider what the two halves of this data set are telling you simultaneously. If the acceleration near perihelion is caused by outgassing, then working backwards from the measured thrust gives you a mass estimate of roughly 4.4 times 10 to the 10th kilograms. A relatively small object, consistent with a nucleus a few hundred meters across. The Hubble Space Telescope images from August 2025 gave a nucleus diameter somewhere between 440 meters and 5.6 kilometers, which doesn't narrow it down much. A more detailed model from Forbes et al. In December 2025 suggested 820 to 1,050 meters with a density around 500 kilograms per cubic meter. But that model assumes the acceleration is entirely sublimation-driven. Here's the problem. If that mass estimate is correct, The object should have shown non-gravitational acceleration before perihelion 2. At that size and density, solar pressure and outgassing should have been detectable well before closest solar approach. But 4 months of data from 227 observatories found nothing. So either the object is significantly more massive than the perihelion acceleration implies, which means something other than outgassing is driving the thrust, or the activity genuinely switched on abruptly at perihelion in a way that current models don't fully account for. Both possibilities are live in the literature right now. There's a parameter in the dataset that doesn't fit cleanly into either scenario. We'll come back to it. Meanwhile, every instrument that could have resolved this is running into its own wall. The Hubble images from December 27, 2025 showed 3 symmetrically positioned jets when processed through the Larsen-Sechenina filter. That geometry is unusual. It's not impossible for a comet nucleus. Jason Wright at Penn State noted that comets behave unpredictably, like cats. But it isn't what you'd expect from a simple rotating, outgassing body. No consensus has formed around what produces that pattern. JUICE, the ESA spacecraft currently en route to Jupiter, observed 3 I-Atlas in November 2025 using multiple instruments: cameras, spectrometers, particle detectors. Most of that data didn't reach Earth until February 2026. The instrument teams are still working through it. Juno is in the Jupiter system right now but has insufficient propellant to redirect its orbit, and its primary engine has been non-operational since 2022. Europa Clipper is in the vicinity. No observational data from it has been published in connection with this object. Every one of those instruments is working at the edge of its operational envelope. The results are partial, delayed, or constrained by hardware that was never designed for this scenario. That's why JPL Horizons after March 16, 2026 will be more informative than any press conference. Here's what actually happens today. 3 I-Atlas crosses the Hill sphere boundary at 53.445 million kilometers. 57,000 kilometers inside the gravitational domain of Jupiter, well within the margin of our current positional uncertainty of plus or minus 600 kilometers. It passes through at 66 kilometers per second, relative to Jupiter. The escape velocity at that distance from Jupiter is 2.2 kilometers per second. It cannot be captured, but it will be deflected. The post-encounter trajectory will be updated in JPL Horizons within days. That updated trajectory encodes the integral of every gravitational force the object experienced inside the Hill sphere. If the measured deflection matches what you'd predict from the current best-fit mass models derived from the non-gravitational acceleration and the nucleus size estimates, then those models are consistent, and the story simplifies. If the deflection is measurably different, then at least one of the inputs is wrong. Either the mass estimate derived from the perihelion outgassing is off, or the assumed density is off, or the nucleus size range from Hubble is off, or the non-gravitational acceleration is not purely sublimation, which means the force budget for this object doesn't close on a simple cometary model. None of those outcomes require extraordinary explanations. All of them would tell us something we don't currently know. After today, the object moves on toward Gemini. The angular diameter will shrink past any useful ground-based resolution. The window for this kind of measurement, using Jupiter's gravity as a reference instrument, closes permanently. In a few months, the object will be too faint for most facilities. In a year, it will be beyond practical reach entirely. There were 3 interstellar objects detected crossing this solar system. Oumuamua passed through in 2017 without us having the infrastructure to understand it properly. Borisov in 2019 was better observed, but still left the system before we could characterize its nucleus independently. 3 I-Atlas is the third, and today is the one moment in its transit when an unambiguous gravitational measurement is possible without sending anything to intercept it. After March 16, 2026, the data exists. The question is what it says. So, if the measured deflection doesn't match the model, if the numbers that come out of JPL Horizons in the next few days require a revision, which parameter do you think gives first? the mass derived from the acceleration, the density assumed by Forbes et al., or something in how we're modeling the non-gravitational force itself? That's not a rhetorical question. I'm genuinely curious which end of this you think is the weak link.